In 2021, astronomers scanning the deep sky found a bizarre cosmic mystery: enormous, invisible rings of energy hiding in the darkness between galaxies. They named these structures odd radio circles, or ORCs. They are gigantic, spanning hundreds of kiloparsecs across, vastly larger than our entire Milky Way. And they share one incredibly precise feature. Almost every known ORC has a massive, early-type galaxy sitting perfectly dead center, right in the middle of the ring like a bullseye. Researchers quickly built a baseline model. If you found an ORC, it was expected to be massive and have a host galaxy anchoring its core. The classification seemed neatly settled. But recently, a single observation from a new sky survey challenged that framework. While inspecting data from the LOFAR 2-meter sky survey, astronomers flagged a strange new radio source, officially named J1248 plus 4826. The very first problem was its size. The ring measures just 30 kiloparsecs across. That is a fraction of the size of any previously recorded odd radio circle. The second major problem was its geometry. The host galaxy isn't in the middle. Instead, it sits pushed entirely out to the outer edge of the ring. This diagram compares the two models side by side. You have the standard massive ORCs with a centered core on one side, and this new compact edge-heavy structure on the other. If J1248 is confirmed as an ORC, it suggests that the current population of these objects may only represent the extreme upper end of a much broader, more diverse family. To figure out what this anomaly is, physicists first compared it to other known cosmic structures. Suspect number 1, a cluster radio halo. This visualization illustrates the brightness distribution of both shapes. Halos are massive fields of radiation that peak in brightness at their center, but the data shows this new object is an edge-brightened ring. The interior is hollow. Suspect number 2, a radio lobe. These are massive plumes of energy created by jets blasting out from an active black hole. But radio lobes universally appear as mirrored pairs, one on each side of the host galaxy. J1248 is a solitary, isolated ring. Suspect number 3, the fading remains of a dying radio galaxy. A dying radio galaxy requires an active galactic nucleus to have recently powered it. Observations of the host galaxy show no ongoing core activity to support this idea. With these established models failing to explain the data, researchers turned toward a more complex origin story involving ancient, hidden material. They found an answer by looking into the deep past. Billions of years ago, an active supermassive black hole was ejecting a massive cloud of superheated plasma into deep space. Over time, the black hole exhausted its fuel and went dormant. The expelled plasma cooled down, lost its energy, and faded into total invisibility. Astronomers call this dead, lingering cosmic cloud fossil plasma. It simply drifts in the darkness, undetected. Fast forward to a more recent era. Neighboring galaxies within this local group began to drift closer together, their gravity pulling them into an interacting dance. As these massive bodies move and collide, they generate kinetic shock waves that ripple outward through the space of the galaxy group. This vector animation maps out the crucial collision point. These kinetic shock waves slam into the invisible fossil plasma, re-energizing the dead particles until they glow once again in the radio spectrum. This strange off-center structure is actually a preserved ancient fossil that has been shocked back to life by galactic collisions. The existence of this tiny radio circle reveals a hidden geography. The voids between galaxies can hold massive reservoirs of dead plasma, waiting for a physical spark to become visible. And because this object is so compact, it implies that countless other tiny odd radio circles likely exist everywhere. They're simply currently hidden just beyond the resolution limits of our current telescopes. We often picture the cosmos as a static painting. Observations like this reveal it to be a dynamic, ever-churning recycling engine. Finding the smallest radio circle highlights how the universe can conserve and recycle its material. Even the ancient, dead breath of a black hole can be shocked, revived, and reborn into something new. Picture a car dashboard hitting 175 degrees in direct summer sunlight. Now, scale that heat up to a planet the size of Saturn. To understand why a 175-degree gas giant is so unusual, we have to look at the ones we know best. In our own solar system, gas giants like Jupiter and Saturn orbit far from the sun, keeping them in a deep freeze, hundreds of degrees below zero. Outside our solar system, astronomers regularly find the opposite extreme, planets we call hot Jupiters. Because they orbit tightly against their host stars, their atmospheres are scorched at thousands of degrees. This leaves us with a stark binary in the observational record: freezing cold or blisteringly hot. Gas giants that sit exactly in the middle of these temperature ranges are incredibly rare, leaving a massive blank spot in our timeline of how these planetary bodies form. That blank spot is why a newly observed planet called TOI 199b is a crucial target. Finding and sampling the air of a warm, middle-ground world finally gives astronomers the missing data point needed to figure out exactly how gas giants grow and mature. Located about 330 light-years from Earth, TOI 199b is the first temperate giant exoplanet to have its atmosphere read in detailed chemical focus. To pull this off, astronomers used NASA's James Webb Space Telescope. Its massive array of gold mirrors is specifically designed to detect incredibly faint infrared signals from across the galaxy. To capture those signals, the orbital timing has to be perfect. The telescope must stare at the host star and wait for TOI 199b to cross directly in front of it, creating a miniature eclipse that filters starlight right through the planet's alien air. Because of its wider orbit, TOI 199b takes a grueling 7 hours to complete this crossing. For comparison, hot Jupiters whip around their stars so quickly that their transits can be over in less than an hour. That long 7-hour window is exactly what the research team needed. It allowed the telescope to gather enough sustained data to measure the star's normal baseline light, and then track exactly how that light changed as it pushed through the planetary atmosphere. The process used to measure these changes is called transmission spectroscopy. It is the core scientific technique for figuring out what an alien sky is actually made of. JWST acts like a sensitive prism, splitting starlight passing through the exoplanet's atmosphere into component wavelengths. Specific elements block specific light, creating dark gaps, a chemical barcode. For TOI 199b, this barcode perfectly matched the fingerprint for methane. Alongside that methane signature, the filtered starlight also contained fainter, distinct markers pointing to ammonia and carbon dioxide swirling in the atmospheric mix. Finding this exact blend of gases provides the first physical confirmation that our predictive models for temperate gas giants are accurate. Moving from theoretical math to a proven, observed methane signature gives astrophysicists a firm, physical foundation to build on. With more observation time, astronomers will be able to take this baseline data and calculate the relative amounts of these different gases to see exactly how they mix in a 175-degree environment. Mapping that precise chemical recipe gives researchers the variables they need to accurately simulate how a warm planetary system physically matures from its original formation over millions of years. This chart plots our known planetary temperatures against their atmospheric makeup. We already had heavy data on the freezing gas giants on the left and the scorching hot Jupiters on the right. TOI 199b fills in that gap right in the middle. Having reliable data across all 3 temperature zones completes the evolutionary map. It gives the scientific community a continuous rulebook for how gas giants behave, no matter how close or far they sit from their stars. The value of this data extends past the behavior of distant alien worlds. The physics of radiative transfer, how specific molecules absorb and re-emit heat, operate the same way whether a planet is a ball of gas or a sphere of rock. Because TOI 199b sits in a temperature range closer to our own than a hot Jupiter, its methane levels provide a real-world laboratory to test how greenhouse gases trap energy at temperate scales, refining the mathematical baselines used in Earth's own climate simulations. The next step for the research team is dedicating more JWST hours to scan the galaxy for other temperate exoplanets. They need to see if TOI 199b's methane-rich sky is unique or a standard feature of warm worlds. By carefully decoding the chemistry of a warm sky 330 light-years away, we are refining the exact scientific tools we need to understand the history, mechanics, and ultimate future of the air we breathe here on Earth. Precision medicine promises to deliver powerful, fragile biological cargo, things like RNA or specific proteins, directly to the exact tissues that need them. To make that journey safely, scientists rely on nanocarriers. These are microscopic armored vehicles, often made from biodegradable polymers like PLGA, designed to shield the drug inside from the body's defenses. But getting the vehicle to the right location is only half the battle. For these therapies to work, doctors need absolute predictable control over when, where, and exactly how much of that payload is released. If we can't reliably predict that release rate, a highly targeted medicine risks becoming useless or actively harmful to the patient. The problem is how researchers actually measure that release. Because these particles are incredibly small, scientists have historically had to test massive populations of them all at once to see what they do. Bulk measurements plot a steady curve, suggesting uniform drug delivery. But this average is an illusion, hiding chaotic extremes. If half the nanoparticles instantly dump their drug and the rest trap it forever, their combined average still mimics that perfectly controlled release. This mathematical blind spot helps explain why highly engineered nanomedicines sometimes trigger unpredictable responses or adverse side effects when they actually enter the human body. To look past that blurred average, researchers at the Institute of Material Science of Barcelona realized they needed a way to track the drug delivery process particle by particle. They turned to a highly advanced microscopy technique called D-storm. Put simply, D-storm allows researchers to pinpoint the exact location of single fluorescent molecules with incredible precision. The team designed a clever dual tagging system. As we see in this model, they attached one brightly colored marker to the polymer shell of the nanocarrier and a second glowing marker to the drug inside, a model protein called albumin. This setup let them watch two independent actions at once: how the outer vehicle dissolves over time and exactly when the glowing cargo escapes. They no longer had to rely on a massive, faceless crowd. Now they could interrogate the precise behavior of individual delivery vehicles simultaneously. The researchers placed this tagged population under the microscope and continuously tracked their evolution over a span of 30 days. At first, they watched the physical transformation. As days passed, the particles absorbed water, expanding in size and developing fractures as the polymer degraded. Across the whole group, they noticed an overarching trend: an initial rapid burst of protein escaping in the first few days, tapering off into a slow, sustained trickle. But the true value of the study came from looking closely at the individuals. The behavior from one particle to the next was wildly uneven. Look at this data visualization tracking the individual release rates. Some nanoparticles empty completely in a matter of hours, others release their cargo slowly, and some stubbornly retain their payload indefinitely. If this team had used the conventional methods of the past, every single one of those extreme variations would have been completely invisible. The pristine, uniform behavior scientists had relied on to design therapies simply did not exist. The reality is a chaotic mix of highly individual particle actions. When we zoom back out to the human body, this microscopic chaos has serious implications, especially when doctors are trying to target complex organs like the lungs or the brain. A chaotic payload delivery means one localized area of tissue might get hit with a toxic, overwhelming burst of medicine, while damaged tissue right next door gets absolutely nothing. Yet, uncovering this flaw provides an essential course correction. It equips researchers with a powerful diagnostic tool. The D-storm tracking methodology can now be deployed to evaluate entirely different types of delivery systems currently in development across the industry. To successfully improve tissue regeneration and create highly targeted therapies, future medical engineers must factor in this vast hidden variability. True precision medicine requires us to abandon statistical illusions and start engineering treatments based on the microscopic reality of every single particle. Curious, there is a theoretical finish line in computer science called quantum supremacy. It's the threshold where a quantum computer solves a problem in a fraction of a second that would take a traditional computer an eternity. In March 2025, a group of researchers announced they had crossed that line. They successfully calculated the dynamics of a massive three-dimensional grid of interacting qubits. Their core claim was definitive. This specific calculation was a wall that no classical computer could ever climb over. If true, it meant the machines sitting on our desks and powering our servers had officially reached their limit, rendering them obsolete for the next generation of advanced physics research. To understand why traditional computers struggle with this, we have to look at quantum entanglement. When qubits are entangled, their states are locked together. You can't process them one by one like a neat row of dominoes. Linked networks must be calculated simultaneously, creating a wave function, a massive mathematical object describing the entire system. It scales exponentially. Adding one extra qubit doubles the problem's size. At a few hundred qubits, this data exceeds the physical memory of Earth's most powerful supercomputers. Standard hard drives have a finite amount of silicon and magnetic space. They run out of physical atoms to hold the data long before the math is finished. Classical computing struggled here, not because its processors were slow, but because there wasn't enough physical space in the universe to store the exponential data. But physicists at the Center for Computational Quantum Physics, or CCQ, were skeptical of the March 2025 paper. They wanted to run the math themselves to see if this wall was truly impenetrable. They abandoned the idea of building a bigger hard drive. Instead, they applied a set of advanced mathematical tools known as tensor networks. Think of a tensor network as a zip file for the wave function. It compresses that sprawling exponential data structure into small, interconnected tables of numbers without losing any of the complex entanglement information. This problem, which would overflow a supercomputer, becomes dense and compact enough to fit comfortably inside standard computer memory. To run the numbers, the team paired this modern compression with a 1980s algorithm called belief propagation, which happens to be highly efficient for processing these tight networks. They didn't need to brute force the calculation with a massive machine. They bypassed the physical limits of hardware by changing the fundamental shape of the math. They put this method to the test using a software library called iTensor, running the highly compressed calculations on a completely standard personal laptop. The laptop chugged through the math and successfully simulated the dynamics of a system containing hundreds of interacting qubits. When they checked their final results, the output exactly matched the data produced by the multi-million-dollar quantum computer. Armed with hyper-efficient math, classical computers proved they can still stand toe-to-toe with supposedly superior quantum systems. This successful experiment reframes the relationship between classical and quantum computing. These fields share a deep synergy, with each approach informing the development of the other. This classical software lowers the barrier to entry for scientists everywhere. You can write code and test complex quantum dynamics right from your desk, without needing a sterile, super-cooled lab or an expensive quantum processor. The CCQ team is already looking at their next frontier, adapting this compression to simulate how electrons move and jump between sites within quantum materials. Tracking moving electrons is a much heavier, more daunting mathematical problem, but solving it provides the blueprint for engineering advanced superconductors. The age of the quantum computer is coming, but total supremacy hasn't arrived yet. We haven't reached the limits of classical computing. Our everyday machines just learned a new way to fight back. Modern materials science operates at an incomprehensible scale. Engineers are attempting to build entirely new substances from the bottom up, particle by particle. But for decades, those engineers have been trapped by a severe structural limitation, relying on just two basic blueprints. On one end of the spectrum is pure order. Think of tightly packed, perfectly uniform crystalline patterns repeating flawlessly in every direction. On the opposite end is pure chaos, completely random, highly disorganized scatterings of particles suspended in a liquid. Restricting design to these binary extremes puts a hard ceiling on what synthetic materials can do. If you can only build with perfect rigidity or total randomness, you lock yourself out of the vast array of physical properties that exist in between. Nature, however, doesn't build at the extremes. Take human bone, which achieves remarkable strength and flexibility by thriving in the messy middle. If you zoom in on bone tissue, you'll find curved nanocrystals merging into twisted plates, which then weave themselves through tangled filaments of protein. It is a highly efficient system of patterns nested within patterns. Physics Nobel laureate Murray Gell-Mann was the first to recognize that this highly functional middle ground had a specific name. He called it complexity. This theoretical chart, known as the Gell-Mann curve, illustrates his concept. Along the bottom, we track a material's structure from pure order to pure chaos. The functionality line shows a distinct peak right in the center, where optimal capabilities emerge. But Gell-Mann's curve was entirely philosophical, lacking any measurable scale to tell an engineer exactly where that middle ground lived. Without a mathematical ruler to quantify complexity, engineers couldn't deliberately target that peak. Creating an advanced material meant relying on trial, error, and accidental discovery. Recently, a research team spanning the University of Michigan, USC, and the University of Illinois figured out how to turn subjective complexity into a hard, calculable metric. They did this by borrowing a concept called graph theory, a mathematical framework traditionally used to map out vast forest ecosystems or track human interactions across social networks. To apply this, researchers defined a single physical nanoparticle as a node. When a second particle interacts, they snap a line between them, creating an edge. Translating particles into a network of nodes and edges maps the invisible forces governing the entire material. The researchers used transmission electron microscope images to map the interactions of thousands of particles, revealing a structural blueprint that defines complexity. They identified ordered components, tightly packed clusters behaving like miniature crystals. Connecting them are chaotic components, sprawling bridges of particles spanning empty space. By calculating how interactions spread, the team condenses this sprawling network into a single value. Complexity is finally a point on a chart. To prove this new math works outside of a computer simulation, the researchers applied it to standard gold. Normally, when gold nanoparticles are randomly distributed and floating in liquid, they only weakly reflect green light. Using their metric, the team forced the gold into that optimal, messy middle, building a loose network of interconnected crystal clusters. The structure suddenly gained the ability to strongly reflect infrared light, an optical feat that is completely impossible for standard gold to achieve on its own. By manipulating the complexity of the internal structure, they dictated the physical capabilities of the material itself. The abstract math produced a tangible, real-world physical property. The same complexity metric accurately predicts the behavior of other materials, such as the tin-doped indium oxide used in modern touchscreens. Structural complexity is no longer a theoretical bottleneck. It is a precise, tunable dial on an engineer's dashboard, ready to be adjusted for specific applications. By mathematically balancing order and chaos at the nanoscale, engineers no longer have to wait to discover materials with unique properties. They can simply design them. If you dive into a black hole, you eventually reach a point where the rules of the universe stop working. It is an environment so extreme that matter is forced into states our current mathematics simply cannot describe. Under Einstein's theory of general relativity, a black hole is a one-way path to a dead end. Gravity becomes so powerful that nothing inside the event horizon can push back against the collapse. This forces matter into one of two fates. It either hits a curvature singularity, a point where density becomes infinite and space effectively ends, or it passes a Cauchy horizon, a boundary where the future becomes mathematically impossible to predict. For decades, these dead ends were considered unavoidable. Roger Penrose proved that as long as gravity remains an attractive force, the interior of a black hole must be incomplete. Space-time simply stops. To resolve this breakdown at the center of black holes, physicists believed they had to invent an entirely new theory of quantum gravity. Without it, the laws of physics remain broken at the most critical points in the universe. Theoretical physicist Francesco Di Filippo re-examined this problem using Penrose diagrams. These are mathematical maps that compress the history of the universe onto a single page to study a black hole's global structure. Di Filippo's analysis suggests that previous models were missing a key factor, the subtle effects described by Stephen Hawking's radiation theory. Hawking radiation is a quantum process where black holes slowly lose mass and energy. It means they aren't static objects, but regions that are constantly, if slowly, leaking. Because this energy loss is so incredibly small, most physicists assumed it was too weak to influence the massive gravitational collapse happening deep inside the hole. To see why, look at a charged black hole. It generates electromagnetic repulsion that pushes outward, fighting gravity. Alone, this charge isn't enough to stop the collapse. Even adding the energy leak from Hawking radiation, gravity still wins, crushing the interior into a singularity. However, Di Filippo found these forces amplify one another. Repulsion and Hawking radiation join together to create a massive outward pressure. This combined force forms a barrier that is actually strong enough to halt the collapse entirely. In this model, the singularity never forms because the forces pushing out finally balance the gravity pulling in. If this holds true, the interior of these black holes is very different than we imagined. Space-time does not end, and matter is never crushed into an infinite point. The interior remains regular. This means the laws of physics stay intact. We can use our existing theories to predict what happens inside, rather than watching those theories dissolve into uncertainty. This suggests we might not need a finished theory of quantum gravity to understand the center of a black hole. We may only need to correctly combine the classical and quantum rules we already use today. Currently, this math is proven for black holes with an electrical charge, which are rare in nature. But DiFilippo is now applying this same framework to rotating black holes, replacing the electrical charge variable with angular momentum. Spinning objects create a repulsive outward force that behaves very similarly to the electrical repulsion used in this study. Since almost all black holes in the universe are rotating black holes, this could mean that every one of them contains a stable, regular interior. The universe may have a built-in mechanism that protects spacetime from ever reaching a dead end.